another episode of Undercooled. All of our guests are special, of course, but maybe some are a little more special than others. And today we have a guest who almost needs no introduction, except for one really important point, which it turns out a lot of the world has been pronouncing our guest's name wrong for most of the history of material science and engineering. So we're so happy to have you on the show today. Could you please tell us, for the record, what are you called exactly?
I'm called Bill Callister, not Bill Callister.
And there you have it.
C-A-L-L is call.
Well, Professor Callister, thank you so much for coming to the show today. Very happy to have you. I'll get my quick celebrity moment out of the way, and then we can get to the agenda. So a couple years ago at the North American Materials Education Symposium, which will be at Georgia Tech this summer. Hopefully we'll see a lot of people in the audience there. You took several of us out to dinner, and I have a photo of me at dinner with the man, the myth, the legend. And I show it to my students, and then I tell them things they don't listen to. But the point is, material science can be a small community, and it can actually be very easy to meet people. There's not a lot of layers of separation between all of us. And I think it's really important for students to hear that they should be making friends and that they should be building professional relationships within the field. But that's my pitch out of the way. So if you could first just tell us a little bit about yourself and how did you get into the field of material science?
Well, that's a good question. When I started the university, in high school, when I was a senior, the Russians launched their Sputnik satellite, which was the very first one. So being an engineer and a scientist became very popular, and I was good at English math and chemistry and some of the physical sciences. So everybody said, you ought to be an engineer. It's kind of like Dustin Hoffman in The Graduate, everybody telling him that plastics was important. So I thought I would try engineering, and so I kind of had to declare a major, and I declared chemical engineering. And I went 2 years, and then I took 2 years off and did a church missionary stint. And then when I came back, I thought, I don't want chemical engineering. And I went through the catalog, the university catalog, and I saw that there was a ceramic engineering program. And I remembered that I'd heard one of the professors from that department give a lecture when I was a freshman. So I thought, well, I'll give that a shot. So I signed up for ceramic engineering. At that time, this was in like 1962, there really weren't any materials science and engineering departments, or there were very few. There were ceramics, metallurgy, polymers, and electrical materials. And then they kind of combined those together and formed material science and engineering departments. So my choice at the time was ceramic engineering.
So once you decided to go into ceramics, presumably you started taking courses, and then what was the next step in the trajectory after that?
Well, I finally graduated. It was a very small department. We had 2 faculty members, and I think there were 4 students that graduated the year I graduated. And so my senior year, one of the professors said, you really ought to consider going to graduate school. And I said, well, what's that? And he said, well, you go get a master's and or a PhD. So I asked him where to go, and he said, I'll get you anywhere you want to go. And money was pretty free then for engineering grants. So I applied. And I decided to go to Stanford University. There were 3 reasons for that. One was that it was the closest of my choices. Number 2, the weather was good. Number 3, I had a cousin who lived in the area, in the Bay Area. So I decided to go to Stanford. Do you want me to continue?
Yeah, please do.
Okay. So a lot of graduate students will select their graduate school on the basis of the expertise of the faculty there and the areas of emphasis. And I really didn't know what I wanted to do. So I just went and took the classes I needed to take. They assigned me an advisor. And things at Stanford were a lot different than they were where I did my undergraduate work. There were some really prominent people there. They were very smart. And I'll never forget my very first exam that I took. And one of the questions on that was to solve a problem. And I looked at the question, and there was no equation given. And I looked at that and I said, I can't solve that. There's not an equation. So at the next lecture period, the professor handed back an answer sheet. And lo and behold, you had to take two equations that were kind of unrelated and put them together, and then solving the problem was very easy. And I thought that was very unfair because as an undergraduate, the way things would work, you'd go to class, you'd get a reading assignment, you'd given some homework problems at the end of the chapter. And so what I'd typically do is forget reading the chapter. I'd go to the homework problems. I'd try to find an equation that I need to use to solve the problem. I'd learn what the symbols represented. I'd do a little algebra to get the right dependent parameter, plug in the numbers, and get an answer. Well, on this one, you had to do a little thinking and thinking out of the box, and then I realized that, hey, maybe that's what engineering is about, is coming up with your own equations. So that was kind of a real important moment in my life and a change of mindset.
I'd like to know who was your PhD advisor and what did you do for your PhD?
Okay, his name was David Stevenson. He's since passed away. And we had to do a master's project and write a kind of a mini thesis. And I did that on the influence of, like Molly or something, on the activity of carbon in iron. We did some experiments. It was a continuation of another project he had. I did that, wrote it up, and then he had some money to do some high temperature conductivity or resistivity and Hall measurements on 2,6 semiconducting materials and get an idea of what the defect structure was. And I was kind of excited about this, so we had to have an apparatus set up. Obviously, it had to go to high temperatures. It was made out of, I guess, silica glass. We had to have, we did it also as a function of vapor pressure of the elements. I think we worked on cadmium telluride or cadmium selenide. So we had to have it set up so we could get an atmosphere of those components. Then we made the measurements, and from those you're able to tell what the defect structure of the semiconductor was at elevated temperatures. A lot of work had been done on quenching materials down to room temperature and then making the measurements there. So I did that, I wrote it up, and got a little thesis out of it. But if I was to continue on with that, I had to worry about solid state physics, quantum mechanics, and all that stuff, which was just a mess to me. I didn't understand it. you want to hear about my interviews
Sure.
for a job? Well, I finished my PhD in June of 1971. At that time, there were not a lot of engineering jobs available. But I had a couple of interviews. One of them was with a local company. I won't tell you which one it was. And this was before I graduated. This was just as I was starting my research. So I went to the interview. I was warned that I would have some problems. And sure enough, there were about 5 or 6 materials people there, and they just hammered me to death. They humiliated me. I wasn't very comfortable. I didn't have a lot of confidence, and it is one of the worst experiences of my life. I had another one back east, and I just didn't know what to say. I didn't know how to handle things, and they didn't even send me a rejection letter. But as I was getting into my research, I realized that if you had a PhD in any engineering field, what you do is you have to do research. You have to do research at a university, at a research institute, for a research for a company. And I didn't like research, and I wasn't very good at it. So that was a real crisis for me. I just wanted to excel in something, and I just knew it wouldn't be as material working doing research. So, and then the summer before I started graduate school, I had an opportunity to go back to General Electric's research lab in Schenectady, New York, and spend a summer there. It was great. The research I did was with a real prominent man, and there are lots of things to do in the East. There are a lot of places to visit. So anyway, then I got out. I couldn't get a job, and I was kind of frustrated. I had some little money saved, so I had the opportunity to go to the Orient. So I took a little trip to the Orient with some friends of mine. We went through Taiwan, Hong Kong, even went to Vietnam. Spent a couple of days in Vietnam, which was very interesting, then Bangkok. And they came back, and I did some tutoring, and then a good friend of mine was a school teacher in an elementary school near where I lived, and their principal needed somebody to come and do some activities with the students, so one of which was to teach the 3rd and 4th grade boys how to do sport. That was wonderful. I knew every kid in school. When I walked out on the playground, they just came up and thronged me. So that was a good experience. I played a little softball. I like to play softball, so I did that. And then I needed to get a job. And the next summer, I found out that there was a postdoc available at a university, which I won't mention. And there was some research money that they had just been awarded to do some research on ceramic materials and their corrosion resistance in slags, very high temperatures. And this was some research for a new kind of electrical generating unit that would be operate at higher temperatures than the regular steam generators or whatever. And they would use coal to burn, and then slags would form from the impurities in the coal. And so there was that slag that was in contact with the ceramics. So I needed to design some experiments to measure that corrosion resistance. That power generating system was called magnetohydrodynamics, and I don't know whether you've heard of it, but obviously it didn't take off. So I did that. I started doing that, and then I got fired. Well, my wife doesn't like to use the word fired, but one of the principal investigators told me that I ought to look for another job. And there was some personality stuff involved, and I didn't really get much support from the principal investigators. So I hung around for a couple of years. They needed someone to teach a couple of classes. I did that. And then I had to get another job. So I found out that Mike Mansfield, I don't know if you've heard of Mike, I think he was a senator from Montana. I think he was very high up in the hierarchy of the politics. He was getting ready to retire, so he decided that he needed to give some money, some research money to universities in Montana. So there was some money awarded for research at Montana State in Bozeman, and then there was some money awarded to Montana Tech. Montana Tech is in Butte, Montana. It's the old Montana School of Mines. They had an emphasis on mining, geology, metallurgy, and stuff like that. And the money awarded there was to do exactly the same kind of research I'd done for my postdoc. So they hired me on. And so I hired a fellow to kind of supervise the research that I'd known as a postdoc. And he lined things up. We talked about the experiments, and they were essentially the same as the ones I'd done previously. And then he hired some people, and so we got things going. And then I had to teach classes and do labs and all that stuff. And that's where I really learned material science and engineering. I had to teach a whole bunch of classes, had to have a whole bunch of labs. It wasn't uncommon for me to be preparing a lecture at 11:30 at night for a class that met at 9 o'clock the next morning. I just couldn't wait for holidays to come so I could get ahead a lecture or two. So I did that. Butte was kind of an interesting place. It's right on the Continental Divide. Temperatures in the winter get down to minus 50. My apartment was right next to next to Evel Knievel's little ranch that he had. And they'd done underground mining for years. They'd given that up, and they had a big open pit copper mine. I think it was run by Anaconda. So anyway, that was a pretty good experience. But Butte just wasn't the kind of place I wanted to settle down and live. So after 3 years, I decided I need to go back to Utah. So I didn't know what to do, and I kind of liked teaching, so I had some contacts at Brigham Young University in Provo, Utah, which is about 40 miles south of Salt Lake. And they had an instructional science PhD program. So I applied to get into it, and I was accepted. And then I had a good friend from graduate school who was in mechanical engineering. And the professor that taught the metallurgy and materials classes had to take a leave for 3 years to do a church assignment. They were desperate for somebody to teach their materials metallurgy classes. So I decided to take that job. They said it will be only for 3 years. We can only guarantee it for 3 years. So I took the job and gave up on the instructional science business, which is probably good. And I just taught they had a couple of materials classes. It was interesting. They had one for freshman students, which was an introductory course, and then they had one for junior students, which was an introductory course that was a little more advanced. They had labs with the courses, and then I ended up teaching a corrosion class. And then about 6 weeks after I started teaching there, I was in my office one day, and this book salesman came in, and they called him a book rep from one of the big publishing companies, and he said, what classes you teaching? So I told him, and he said, what books do you use? And I told him. He said, what do you think of them? And I said, well, I really don't like them. They don't do what I want. So he said, would you like to write a book? So I said, sure. Everybody wants to write a book. So he said, write a couple of chapters and then send them to me. We will send them out to be reviewed. And if the reviews are positive, we'll sign you up. So that year I put together, I don't know, 2 or 3 chapters. And on Labor Day of the next September, I sent them to him. And the reviews were good. So on, I think it was January 1st, 1980, I signed a contract to write a book. So I continued at BYU, and I class tested some of the stuff I'd done. And then at the end of 3 years, they didn't want to keep me on, so I had to leave. I wasn't married. I moved back to Salt Lake and moved in with my parents. And I spent the next 3 years working on writing the textbook. And it was nice to have my time free. I kind of freeloaded off my parents. I helped them off with, I did mow the lawn, stuff like that. So, just as I was kind of finishing up the book, they needed somebody at the University of Utah to teach an undergraduate class or two. So I started doing that. And then eventually that worked into a full-time position. Some of the faculty wanted to buy back some of their teaching time for research, and so I needed somebody to teach the basic courses. So ultimately that turned into a full-time job, and I did some undergraduate advising. But then getting back to the publication of the book, writing a textbook is very complicated, or there's a lot to it. If somebody tells me they want to do a textbook, I say, you'd better multiply the time that you think it's going to take by a factor of 3. You not only have to write things out, you have to get illustrations. I like to draw mine because I wanted the way I wanted. You have to get photographs. You have to compile tables. And the worst one was getting copyright permissions. So I had to learn the copyright permission game, what you needed to get permission for and what you didn't. So I prepared my manuscript. I think they had it reviewed, and there were a few good comments on what I should do. And then the book goes into production. And with production, they do the proofs that all the text is on. In those days, I think they did it manually. I'd get these page proofs, and they just reeked of cigarette smoke. So obviously they were doing it manually. So I had to proofread all that, and that's just tedious and terrible, but it has to be done. You know what it's like if you get a textbook, you find an error in it, and you think, gee, the textbook's horrible. So I didn't want any of those. And then they'd send me the illustrations. They would draw the illustrations, and they'd send them to me, and I'd review them and the tables and everything. And then they put it together, and I'd have to do the final page proofs to see that all was the way I wanted. So I did that, and then came indexing. And indexing is horrible, and most publishers want a professional indexer to do it, but they have no idea of the context of the terms. So I resolved myself that I was going to do it myself. So I got 3x5 index cards and did my indexing from those. It took me about 6 weeks. So I got that done, and the book was pretty well worked out. And then the next thing was they said, oh, you need to do a solutions manual. And usually, if you saw any solutions manuals from the 1960s or 70s, they were handwritten. Well, I said, I don't like that. It doesn't look very good. So I said, I'm going to try to word process mine. And this was like 1985. And you had to get a dedicated computer that did word processing. Oh, I forgot to tell you about my doing my manuscript. I had an Atari computer that had a word processing program that went with it. For the monitor, I used my television, and when it would format every character at a time. You could see all the characters rastering down the television screen. But anyway, our department had a word processor that had an equation editor. So I went in and did my solutions manual. I don't know how long it took, but I'm willing to bet that it was probably the first word processed solutions manual that was ever done. So that turned out fine. Then I think my book was published in February of 1985. And right after that, I think it was in May, I got the flu or a cold, and I was sick for a couple weeks. And then I got better, and then a week later I got it again. And this just kind of went on and on and on. And then I just didn't have any energy. I couldn't get out of bed. My brother's a doctor, and so I had him give me some hemoglobin injections, and that didn't work. So finally, after about 6 months, I went to a doctor. And the doctor said, well, we got to do some tests. So I did some tests, and I went back to see him. He says, your neurochemistry is messed up. So he said, I'll prescribe you this stuff. You're going to have to take it for 6 months, and then we can taper you off on it. Well, it was an antidepressant they gave me. So I was just worn out from doing the book, the solutions manual. And so I was okay after that. I didn't realize that when you do a textbook, you do additional editions of it. I thought the first edition was all over. And then about 3 or 4 years later, my publisher had me come back to their office, and they got one of their big shots to talk me into doing a second edition. He actually later became the CEO of the company. So I got in and started doing a new edition. I got a lot of feedback. I decided to add some things. And so we came out with the second edition. And I found out that the thing I liked to do most with these books was do the covers. I designed almost all of the covers in my books. And then would send a kind of a raw image, and then they had a professional professional artist put in do a rendering of it. So anyway, I just kept doing that. I got a co-author, Dave Rethwich, who's been very, very good. I had some very good editors for the first several editions of my book. They were great to work with. We just did some fun things. I came out with an alternate edition, which we called Fundamentals of Material Science and Engineering, and it was organized a little differently than the introduction to the book. The introduction book took, for metals, discussed the crystal structures, the diffusion, mechanical properties, and so on. And then we did that for ceramics, and then we did that for polymers. In the new one, we took and did the structures of metal, ceramics, polymers, all together, properties together, and phase diagrams. And I just love this work. I think I had the skill set that was right for it. I'm really not too bright. To be honest with you, I'm not too bright. And that was an asset because I could relate to the problems that students had understanding material. And I think a lot of textbook authors write their books for their peers. And I remember when I was, I'd never had anything on polymers, and you know a little bit about polymers. They're really complicated. And I'd go to the literature, and they had different terminology, and it was really crazy. I couldn't find a diagram of a spherulite. I couldn't find that anywhere. And finally, when I was teaching at the University of Utah, one of the graduate students said, I can get you one of those from a thesis. So, and I just loved what I was doing. I was kind of compulsive about getting things correct. There's kind of an artistic bent in doing illustrations, and there's some real challenges there. And then as time went on, I started incorporating new things in my book. I had learning objectives, and I had these concept check questions, and I had materials of importance, things where I'd highlight a particular material or kind of material and why were they are for an application. For example, I had one on coins, the kinds of metal alloys they use for coins. I have one on shape memory alloys and what goes on with them. And then I had one for catalytic converters, how they work and about defects. And then we got into the digital area, and we put together some animations and dislocations and planes and directions and crystal structures, polymer structures, and that was kind of fun. And then my publisher came up with some new things. There was, I won't tell you what it's called, but it was kind of like Blackboard or something like that, and they had algorithmic problems. The computer would generate them, and they'd give random values to the parameters in the problem, and so every student would have to take the homework or do a test on using their computer, and every student would get a different answer. And it was I had to help get that going. I had to review what other people did, and it was kind of a nightmare.
It was Wiley Plus.
Yeah, that's right.
Yes, I suffered through that.
Did you?
Yeah.
Well, now what they've done is they've got a Zybook, and I don't know whether you're familiar with that. A Zybook, at the end of each section, they have some questions. And the questions are multiple choice, true, false, or fill in the blank. And they're good in that it forces the students to read the book. But if you want, and I'll maybe get into this later, if you really want students to learn concepts, and there's a lot of concepts there, they don't learn them by answering multiple choice, true, false, or fill in the blank questions. The Zybook is great for computer science. It's great for math, but they have all these rules, and it'll kind of work for material science. Oh, well, let's see, what else? What else have we done?
I got to tell you one thing, Bill.
Okay.
I've never had a course in polymers ever. And everything I know about polymers, I learned from teaching from your book.
Oh, really?
And
Thank
I got
you.
to say, I've now worked with companies leading teams on for companies that do polymers. And the insight that I got from your book allows me to create and innovate and actually make real contributions. And I'm a total poser because I never learned any of this stuff except at the introductory level. But I really need to give you credit for laying out the concepts that are important for polymers. And little things like, you'll have a polymer and you think about diffusion through a polymer. And I'm shocked that a lot of people who do polymers for a living, but maybe aren't material scientists, just say, oh, everything goes right through polymers because they're so light. And I'm like, what are you talking about? Those atoms are really tight. Very little, maybe ions go through. But how are you going to get a big organic molecule to go through high density polyethylene? It's not easy. And if you actually look at the structure, you have some really nice illustrations of, the crystalline regions and then the amorphous high molecule regions. And it just gives me an intuition of what's going on based on other materials that actually allows me to operate professionally with only that background. Now, yeah, it might help that I had some colleagues whose pictures are in your books. One of them is Dick Robertson. You have your picture of crazing.
Right.
Dick Robertson, when he was at Ford, there's a classic picture of crazing that's in your book. But, and of course, if you get craze cracks, then you have a fast diffusion path because all of a sudden you have big voids in the material. But it's given me the ability to work in that field just by teaching your book. So thank you.
Well, thank you.
Well, I don't want to turn this into a one-upping contest, but in this case, I can beat Steve, so I'm going to. I've never taken a materials class at all. But since I got hired in a materials department, I said I should probably learn this stuff at some point. And so my first summer on the job, I sat down with, I think it was the 8th edition of Callister, and I just worked through the book for the summer. And that was how I learned material science, which was great because I was expected to teach it in the fall. And, necessity certainly led to the motivation to get it done. But my foundation in this field was entirely from your book. And I'm very grateful to have had that resource to get started in this field.
Thank you.
Another example. So in the research I'm doing with ultra-fast lasers and materials, we started realizing we were getting incredible amounts of mass transport. And it was all because the high field from these laser pulses ripped electrons out of the valence level on time scales shorter than phonons. So in 3 femtoseconds, the electrons would leave. But the atoms were already vibrating at room temperature. But when the electrons from the valence level go, what happens to your interatomic potential, right? You lose the attractive part. So there's no restoring force. So the atoms won't come back. So if they're vibrating, if an atom's moving away, the laser comes and snips those electrons, excites them. The ion is just going to drift. And so we started realizing we're making Frankel pairs. We're making a interstitial and a vacancy that are now so far apart because it's halfway across the unit cell that they're dissociated. At any rate, we started seeing structures form that could only be forming by the transport of these defects. And when we calculated it, we said, well, what temperature, what diffusion coefficient could we apply to explain that? And we were getting liquid-like diffusion, but it was not melted. And we're going like, oh my God, this is like 14 to 20 orders of magnitude higher mass transport. I'm going like, how can that be? And then I went back, I said, let me go look at a diffusion table. And I looked at one of your diffusion tables, and sure enough, diffusion goes like up to 80 orders of magnitude from absolute zero to melt.
Yeah.
And there it was. And I had never noticed that in your book, but it was there. And so it is a lot of mass transport, but it really helps to bring it back down to simple fundamentals to actually understand it. And all I needed for diffusion was your book. I didn't have to go to anything fancier because it was all there.
Well, good.
A lot of times when students are encountering problems in their upper level courses, very frequently the solution is in the introductory textbook. And this is true whether we're talking about materials or chemistry or physics, geology, whatever it is. And to remind juniors and seniors and even graduate students that that first text that they used has most of the answers they're actually going to need for understanding the ideas and the concepts that are relevant to their professional work, I think is something that students can easily lose track of, and it's important for us to remind them that they have those foundational resources. And
The foundations are important, the basic concepts.
Well, and material science is much more like physics than other engineering disciplines in that it's all about mechanisms. It's all about atomistic mechanisms. We don't make, we don't have constitutive equations like the mechanical engineers do. We have fundamental mechanisms, and we're constantly building new mechanisms because we haven't discovered all of them. But we know the basic ones that are all laid out very nicely in your book. Vacancy diffusion or interstitial diffusion, very different. But, those core conceptual ideas, which, I like to think of as atomistic mechanisms, is kind of what sets materials science apart from a lot of other engineering. And it also is what gives us the ability to create and innovate and design materials that have never existed before. So focusing on those basic conceptual ideas of what is a mechanism, right?
Yep.
Is really important. And I know you have a lot to say about all these fundamental concepts. So, but that's great. So you spent the rest of your career at University of Utah in materials?
Well, that's kind of interesting. I eventually, like I say, I essentially oversaw the undergraduate program for a while, and there were some problems in the department, and I just said I got to leave. So 30 years ago, I left the department, and then I got an adjunct appointment in another department there. And now they've combined those departments together, so I still have an adjunct appointment. But I don't do very much. I used to go to graduation. I'd go to one dinner. I'm going to have lunch in a couple of weeks with the chair of the department, and so I do that. But I just decided I was going to spend time with my books. There's still some things I would want to do. I had the plan of having an online module for each of the other engineering disciplines, one for mechanical, one for civil, one for electrical, one for chemical, and then one for bioengineering. I got the mechanical engineering one done, and then I started on bioengineering, biomaterials, and I got all caught up in that, and I was going to do a book on biomaterials, which would have been really stupid. So I had to give up on that, and I haven't done the other engineering disciplines. But I thought, that's if you can get the basic fundamentals in the book, and then there are certain things that chemical engineers need to know. They're different what mechanical engineers do. But I'll probably never get those done. I'm 85 years old. In 5 years, I'm probably going to be gone, or at least not doing very much. And then I've got my stuff with my concept business that I've got to work on. So, I'm going to be busy, I think. So.
Well, why don't you tell us about your ideas about concepts? And from hearing your talks, it's a little more complicated than it's concept relationships.
Yeah, do you want me to put on do my little slide thing?
Yeah.
For a long time, I have been concerned, as a student and as a graduate student as an instructor about the way courses were designed. And I came to the conclusion that there were some deficiencies. Now let me just see how in these introductory course and other courses, that the way things were organized didn't make sense. There seemed to be a lack of relevance to the subject matter, in real life. And then there was very little emphasis devoted to understanding concepts. Most of what was done in the courses was you'd solve problems for numerical answers. So the student would have to memorize the equation, learn what the symbols meant, do some algebra, plug in the numbers, and get an answer. So essentially, students were learning to memorize equations and solving problems from them, and it developed their problem-solving skills. However, materials is, from a pedagogical perspective, consists of a huge number of concepts, probably maybe hundreds or thousands: atomic bonding, crystal structure, dislocation, microstructure, phase transformations, corrosion, and so on. And I would argue that these are important to a materials scientist engineer's education. In some chapters of my book, there are absolutely no equations. And I think what typically instructors do in those situations is they tell the students to read over that material, and then maybe there will be a question on the exam, a question or two on the exam. And learning and understanding concepts is highly neglected, and coming to understand concepts and their relationships is more important than learning and memorizing facts. Concept understanding is, as I said, is more than memorization. It involves cognitive activities in the brain that are subconscious processes, discovering and processing new ideas, reorganizing knowledge and connections, and changing their thinking patterns. And then these things are instigated by conscious things that students do: deep thinking and pondering, self-reflection, and critical thinking. So the obvious challenge is to design, for concept understanding, is to design homework problems that provoke these kinds of thinking processes and cognitive activities. In other words, we got to force students to think the things we want them to think, which is very, very difficult. And then I wondered what kind of assignments accomplish this goal. And I pondered and thought about this for a long time. And then on August 26, 2022, almost 3 years ago, at 10 o'clock in the morning, I was in my bed doing some thinking, and I came up with an idea, or a couple of ideas, of kinds of activities to lead to concept understanding. And during the last 3 years, I've done a lot of thinking about this. I made a lot of changes. Interestingly enough, I'd get ideas while I was in the shower, and I'd have to run right after I got out of the shower and write down my ideas on 3x5 cards. And then I came to the conclusion that there were two types of concept understanding assignment types that students should have. One is understanding individual concepts, and the second is understanding concept relationships. And then I've got a little slide here that kind of shows how I pictured this. There's the individual concept type, and then the relationship type, and there are three subcategories: concept checks, concept maps, and what I call concept vignettes. Let me start out with the individual concept and tell you what kind of assignment, the assignment that I had for that. And this is the procedure for students learning concepts. The students are provided a set of concept-related questions to be answered. Each answer is in the form of a definition, explanation, or description. These answers are found in the textbook or other reference materials, including ChatGPT. The students need to go to these sources, locate the answer. They must think about the answer and form the answer in their minds. And then the answers are to be written in their own words, preferably handwritten, and then submitted digitally to the instructor. So and then the source of each reference that they used was to be cited. So going through and having to find the answers and think about them and write them down, that's why it's best to have them handwritten. I think they probably learn a little better than if they do it digitally. So this is the kind of assignment that I would propose for individual concepts. Let me give you a couple of examples. For example, explain why liquid water expands when it freezes. Describe thermal fatigue failure and explain how it may be prevented. And then define metastable in terms of microstructures. So there are hundreds of these questions you can get. Okay, let me now move on. I should say that I have generated a lot of these questions. I took the learning objectives from my book and just turned them into questions. And there are a lot of other questions like this need to be generated. Now moving on to the understanding concept relationships. In order to understand relationships, students have to exert a greater cognitive effort than just understanding. And then I came up with the idea that maybe there are three different kinds of homework assignments to develop these relationships. There are concept check questions, concept maps, and concept vignettes, which were in that previous slide. For the concept check questions, these will be between two concepts, two or more. I've got to change my page here. The students are to answer questions in which they explain connections between the two concepts. These answers are in the forms of explanations of how and why, comparisons, cause and effect explanations, and they might be answered to required to generate schematic plots and explain them. And then these things have to be in the students' own words. Okay, I'll give you an example. I think I had one of these before in one of the talks, Steve, and it wasn't a very good one. But this is one: do non-crystalline materials exhibit the phenomenon of allotropy or polymorphism? Why or why not? So the students have to understand the concept of polymorphism and about crystallinity in materials. And obviously, if non-crystalline materials don't have a crystal structure, they can't change that crystal structure. Okay, the second kind of relationship exercise is to generate concept maps, diagrams that depict the organizational relationships among or between concepts. I prefer hierarchical and vertical ranking, and that there need to be at least two subtopics. It's really not much of a concept map if it doesn't have more than that. Okay. and then the assignments for these, the students would be provided a list of all the concepts in a map. The arrangement of these concepts would be random. And the assignment is to, first of all, provide a written explanation for each concept, like I did for the single, answer the questions like you did for the single concepts. Then they have to organize the interrelationships in their minds, and then they need to construct the map. Let's see. Okay, I've got an example here for types of magnetism. Okay, so the main category would be types of magnetism, then I've got strong, weak, ferromagnetic, and so on. So the students need to go through and organize these, and the concept map would be something like this. The types, strong, weak, and the three categories under each one. I went through my book, and I could only find about 15 sets of topics that could be used to make concept maps. Another possibility an instructor could use was to assign students to generate concept maps for things that they discuss in class over a period of several weeks. So this would give them an opportunity to organize in their own minds how things tie up together. Okay, now let's go to concept maps. Oh, okay. First of all, the vignettes. These are some deficiencies that some of that I've already mentioned previously with courses. Students find the flow of subject matter confusing. Organizations, they don't understand that, and there's a little sense of relevance. And these vignettes will help to remediate some of these deficiencies. Okay, I decided in order to do this that I needed to kind of come up with a framework to assign questions that would have the students understand these relationships. And I decided to use the paradigm of material science and engineering, which you should know that the material science in a nutshell is 4 words: performance, properties, structure, and processing. Steve, I remember you telling us about a fellow that taught an economics class, and it broke down to like one sentence. And this is what the paradigm is the performance, properties, and structure of materials. And typically, it's presented, these elements are presented in the form of a tetrahedron, which each of these components is at a corner, and sometimes they'll put a characterization in the center. And this is okay to how to represent the paradigm on what it is, but I think there are some relationships between these components, that the performance of a material depends upon its properties. The properties depend upon structure, and structure depends upon how it's processed. So this is kind of how things work, and I kind of have a little slide here showing in a linear fashion this relationship, that the arrows represent how one of these elements relate to another. So processing, structure, and properties. And then I thought, maybe performance can be taken to mean how materials are applied. Rather than using performance, use applications. So I decided, well, let's change it a little bit and say that the applications are dependent on properties and so on. Okay, and then I need to figure out a way to incorporate this dependence of properties or these components into assignments which would lead for them to understand these relationships. And I did this, I decided to use what I call concept vignettes. These are student assignments where the students incorporate these interdependency of components. And I use the term vignette because it's a short narrative created by the students that describes these relationships. And then there are two parts to each vignette. The first part is for each paradigm component, structure, properties, and so on, there would be a set of questions for a specific material or set of materials for or situation or phenomenon. And these questions are answered in the same manner as the concept understanding questions. The students need to find the answers, formulate the answers, and write down the answers in their own words. Okay. Okay, the second part, the purpose is to take these understandings of the individual items and develop student understanding of the dependencies. And I decided that the dependencies would be for pairs of components, like applications and properties, properties and structure and processing, rather than try to put them all together. Here I've got it here, the three pairs. And then at the end, the students need to explain these. And I decided to do these concept questions for Portland cement concrete. Give you an idea how this works. The structure questions I've got: note the difference between cement and concrete. In addition to cement, what are the other three ingredients? Describe other kinds of reinforcements to improve the strength, and then explain the mechanism for each. Processing questions are: describe the steps used to process the ingredients and explain the process of calcination. Property questions are: note three features of Portland cement concrete that make it the most widely used structural materials, and note three limitations of it. And then I like to have application questions that are personal to the students. Cite at least three applications of Portland cement concrete that are important to you. And then, when possible, have a sustainability question. Here, describe a suitable sustainable substitute and explain the features that make it sustainable. Okay. So, I think there's the advantage of using this concept-based learning is that the student gets a sense of relevance, real-life applications. They get a chance to realize the organization scheme and realize that, and actually this whole way of doing things would not be the way the book is organized. You don't start with atomic bonding and so on. And then they develop to think conceptually. I think being able to think conceptually is a mindset on how to solve real-life problems, and then hopefully the writing skills of the students will be improved. Okay, this is kind of where I've gone on this. a lot needs to be done. I've got some of these vignette questions for about maybe 50 or 60 situations. A lot more needs to be done. And like I say, I'm not going to be around too much longer, so I'm going to need some help. Obviously, this approach needs to be incorporated into the classroom, and obviously, it's not going to be the only thing used in the classroom. The students are going to have to solve problems. There are going to be lectures, but it provides a framework for them to come to understand concepts and their relationships. And I think the sequencing of these pairs of paradigm components is important. I would say that the first thing that would want to be done is to have show the relationships between applications and properties, which is fairly simple, and then later on how properties are affected by structural elements, and then finally later on how the structures are dependent upon, or how they're generated on the basis of processing. And I think that some of the real problems with this approach is, number one, the students are going to hate it. Students are not going to want to do this kind of thing. In fact, they're probably engineers because they look at engineering as just solving problems. The second issue would be with how do you grade these things? And I would suggest that there's probably a way using artificial intelligence to grade these answers and to see if they're genuine. And then I've got a little here quote. I think I took this from someone else's book, that when you challenge students with concept-centered learning for the first time, don't expect them to leap to their feet and embrace you with gratitude. They're probably not going to like it. And then here I've got my email address if anyone wants to contact me. So that's my spiel. How do I get out of this?
Oh, you can just don't worry about it. We can listening to what you're saying. You're sort of doing a brute force approach to this.
That's right.
That's going to be really tough to grade. But another approach, of course, is to give students very complex problems that are very open-ended, and impress upon the students that there is no right solution. It's the best solution that matters. So here's a complex problem. Use all the concepts in the book to solve it. Let's see your solution and tell us where you got this solution from, how you used concepts in the book to arrive at your solution to this problem. And it's probably even better if you can make this a team-based activity, because different students will grab onto different concepts differently. And so getting many different viewpoints and having students talk to each other, they can explain these concepts to each other. And that's a really powerful activity, because as you know, you don't really learn anything until you teach it. And if you can set up things like that, they may not hate it so much, but it's really doing exactly what you just laid out. And so I think that would be a process to use these concepts and concept relationships. So maybe you could start by giving a demonstration of how the instructor would solve a complex problem, and talk about taking all these concepts and understanding their relationships in the context of the tetrahedra, and look what we do. Look how we can solve this problem. Even just some things we talked about, what does ultra fast laser irradiation have to do with diffusion?
Hmm.
Right? But it does. Everything does. And you can almost think of any problem that anyone has ever solved. And, you're abstracting these fundamental concepts to find a solution, even inventing new concept relationships,
Hmm.
right?
Well, and that
Because,
takes us all the way back to where the conversation started. It's coming across that problem where you say, oh, I have to combine different ideas that I didn't realize had a relationship to each other. But now here I am, and I have to take these apparently disparate things and find the way to join them to create something new. I mean, that's the essence of what we want our students to be able to do.
yeah, so, something as simple as, we just had a visit from one of our alums who's now the head of materials at Apple. And do you remember when people would put their iPhones in their back pockets and sit down and the phone would bend? They call that bend gate. Well, that's why they hired this person. And, he went there and they said, what do we do? What do we do? How do we solve this problem? And his first question was, well, what alloy are you using? They told him, he goes, well, that's an off the shelf alloy. Of course, that's not going to work. You have to design your own alloy. And they go, you know how to do that? And he goes, yeah, that's what I learned in school. Because you have to, and so you can take something like that or any real problem and talk about how you use the concepts to invent a new material, to design something. You design something, you make something that never really existed before. And I think students will resonate with that, especially if you choose topics that they care about, like sustainability. Your
Well,
problem,
you,
your thing with Portland cement, the sustainability issue. The big problem is all this CO2 comes out. Something like 10% of our CO2 load, man-made CO2 load on the atmosphere, is because of concrete.
yep.
And there are, but once you realize the problem is that calcium carbonate gets changed and the CO2 releases. So you need to start thinking of, well, how can I capture that CO2 and keep it in the concrete and not let it get out to the air? And people have solved this problem and the solutions are out there. The only problem is it costs too much.
Yep.
But that's part of the complex problem. And, how would you capture CO2 coming out? The thing that I would think of is you want a getter, you want something else that's going to react with it and bring it back into the solid state. That's kind of an obvious thing, but, I think that's the way to make this approachable to students because they'll feel empowered if they can use concepts to solve a problem that they care about or think is important or they think they can make them money. Because guess what? If you can figure out a way to capture that CO2 economically, you're going to make millions of dollars.
Well, maybe there could be a combination of what I've done and what you've mentioned, that you could use kind of ask the questions on that problem that would cause them to try to think about relationships.
Yeah.
But you're probably the only one that can come up with a lot of those questions.
Oh, there's a lot of people who can do that. I think that's what's so much fun about, the world we live in. There are so many problems that are just begging to be answered. And why not enlist the help of our students to solve all the world's problems?
Yep. Good idea.
So as we talk about this, we quickly are veering away from the traditional way of teaching where you read a textbook, the professor comes in and bores everybody by lecturing, and then people go home and turn that algorithmic crank to solve problems and do what you thought you were supposed to do when you took your first graduate course at Stanford. And of course, that's not what it's about, right? It's about thinking and relating these concepts to real world problems. So you've been in the textbook business for a long time,
Hmm.
but I think the textbook business as a business is falling apart.
Yeah, it
You know,
is.
things going digital have really rocked the foundations of all publishing. And you already brought up yourself, you're looking for digital answers to add modules. What do you think the next textbook, where do you think these textbooks are going? You think about the future, how are we going to transmit information and communicate these things to our students going forward, given the environment that has been created with the internet, generative AI, and social media, where students learn all their news? They don't read newspapers, they don't read books, they're not reading anymore.
They hate to read.
Yeah, what do we do? So, what is the future of textbooks from your point of view? Because I'd really be interested to hear that.
Well, you know, I just don't know what's going to happen. The textbook publishers haven't known what to do. It's just go digital, and I think they want everything to be digital now, so that they have control over where it goes. You know, I really don't know, but I think, well, students don't like to read. I think, from what I understand, that reading from print, when people read from print, they learn more and retain more than if they read it from a screen. Of course, students don't care much about that. I approached my publisher quite a while ago, and I said, you know, it's nice to have your digital product, but you really ought to have something in print. And I suggested taking my end of chapter summaries, use those, use all the illustrations, photographs, and tables, and put them in a paperback book that sells for $50, so the students would have something. But I don't see that as a solution. I guess I don't know what's going to happen to textbook publishing. It sounds like it's either going to stay where it is or it's going to get worse. My royalties have gone down by a factor of 2 since things went digital. But I don't have a good relationship with my publisher right now. Our correspondence is between my attorney and their attorney. So I don't know what's going to happen. But, Steve, I don't know. There's some things that need to be done. I would hate to see it go out of print. I have no idea. What do you think?
Well, even though we're complaining about students not liking to read, that's different from them being unable to or unwilling to. I mean,
Yeah.
there's certainly going to be arguments to be had in the classroom, but at the end of the day, if it is the optimal way to learn, right? If you create a textbook like you have that's actually readable and worth reading, and where that's the best way to get the information, then that's still going to be a valuable resource to students. We all do things we don't like because they're
Right.
good for us. Sometimes I go running. I hate running, but it's good for me. Sometimes students will read a textbook even if they don't love it because it might be the best resource that they have. And so I think this is part of the challenge for the future textbook, is to make it the best resource that students can access, so that even if they don't love it, they still get value out of it. And unfortunately, printed books, because the world changes so rapidly, just can't keep up in that way
No.
to be valuable the way that they were even 20 years ago, let alone 40.
I've often thought that one way to change this, instead of making students read the textbook, make them write it. And you could do that by taking the images from your textbook and not putting any words in, just printing the images,
Good idea.
and make students write, what do you think this image represents? and how would you use this image to solve problems? And it's kind of something I noticed that when you look at any field, physics or chemistry or material science, what is the same in all of those textbooks are the pictures. Pictures are all the same. They might be reimagined, but they're all the same. And I think you might have seen me do this at a names meeting. I ask everyone in the materials community, take out a piece of paper and draw an interatomic potential. And they all draw it the same way. They draw it energy versus interatomic separation. But that's not what's in your book. You have both. You have, the force.
Force and energy.
Right. And they're, of course, intrinsically related. But why does everyone draw the energy version? And the reason is because that's where we tag our memories to. Because the energy version, the potential well, tells us what the melting point is, the strength of the bonds, the asymmetry of it tells us the thermal expansion, the slope of the attractive part of the potential tells us the stiffness of the bond. We know exactly how to see where the equilibrium position is at any given temperature. So these are iconic images, right? They're like Jungian archetypes, the Ouroboros, and they're very meaningful. And sometimes images are like the Schrodinger equation. The equation itself is like an image, and you tag different parts with what the meaning is, the conceptual underpinning. So what if you made a coffee table book and just made the images, and you use that coffee table book to explain to the students when you lecture or give them problems and show them how to use these pictures, and then make them write the book, the textbook? I don't know how they would use ChatGPT to fake that one, So I don't know. That's just a crazy idea.
I need to think about it. It's a good idea.
Well, I hate to be the bad guy, but we've run out of time for today.
We have. This is a long one.
But
yeah, thank you so much, Bill. Is there anything you want to tell us about what's coming up with you that you want to publicize? I know you're going to be at the names meeting, so I'm really looking forward to seeing you in Atlanta in August.
Yeah, that'll be good. I don't know. I've just got to get back to working on my little project and fine tuning it. And I'm open to any suggestions that you have to suggest, and maybe we can incorporate some of your ideas, Steve, with what I'm doing.
Sure. And, if you listen to the last few undercooled sessions, we talked to Robert Talbert, who's been very influential in helping us think about grading. And he brought up the whole concept of clearly stating standards and choosing very carefully what those standards are, because that's what you should be measuring for the growth of a student's understanding or ability to advance their field. And your concepts fit those very nicely, I think. We also talked to Taylor Sparks. We saw him at the TMS meeting, and he said that you're his neighbor.
That's right. He lives about 3 blocks from me, 3 or 4 blocks. Yeah.
So he's doing some interesting stuff, and of course he has a podcast that's fascinating. He talked very kindly of you, and he says hello. And,
I don't see him too often, but I should.
Yeah, and so anyway, let's keep talking about all these things.
Okay. Yeah, and please let me know if you have any suggestions, or if you want to help, or whatever.
Well, let's talk in Atlanta, because Tim's going to be there. I'm going to be there, and so
it'd be a great chance to put our heads together.
Yeah.
Well, thank you for the opportunity to do this podcast. It's an honor for me to be able to.
Well, the honor is ours.
Oh, absolutely. It's been such a pleasure to hear the stories of how all this came to be.
Yeah.
You were really a leader in getting us here.
Well, it's been fun. It's been a great career. It really has been. I went from utter despair when I got out of graduate school to being happy now. So
Well, that's great.
We'll leave
Well,
that as the takeaway message for the students in the audience. Someday, you too will be successful, even if you're
That's
not
right.
sure about it right now.
Right.
good.
All right.
Well, thank you, and we'll stay in touch.
All right.
Excellent.
Thank you very
Thanks so
much.
much.
We'll see you later.
Okay.
See you next
Bye-bye.
time.